So what is the wave function that we have? We must have a wave function now that is symmetric and built with e to the kx, kappa x, and e to the minus kappa x. This is the only possibility, e to the minus kappa absolute value of x. This is psi of x for x different from 0. This is, as you can quickly see, this is e to the minus kappa x when x is positive, a e to the kappa x when x is negative, and both of them decay. The first exponential negative is the standard decaying exponential to the right. The one with positive, well, here x is negative as you go all the way to the left. This one decays as well. And this thing plotted is a decaying exponential with amplitude a, like that, and a decaying exponential with amplitude a, and a singularity there, which is what you would have expected. So this seems to be on the right track. It's a continuous wave function. The wave function cannot fail to be continuous. That's a complete disaster. The Schrödinger equation could not be satisfied. So this is our discontinuous wave function. So at this moment, you really haven't yet used the delta function. The delta function with intensity alpha down. I should have made a comment that it's very nice that alpha appeared here in the numerator. If it would have appeared in the denominator, I would be telling you that I think this problem is not going to have a solution. Why? Because if it appears in the numerator, it means that as the delta function potential is becoming stronger and stronger, the bound state is getting deeper and deeper, which is what you would expect. But if it would be in the numerator, in the denominator, as the potential gets deeper and deeper, the bound state is going up. That makes no sense whatsoever. So it's good that it appeared there. It's a sign that things are in reasonable conditions. So now we really have to face the delta function. And this is a procedure you're going to do many times in this course. So look at it and do it again and again until you're very comfortable with it. It's the issue of discovering what kind of discontinuity you can have with a delta function. And it's a discontinuity in the derivative. So let's quantify it. So here it is. We begin with the Schrödinger equation again. But I will write now the potential term as well. The potential is plus v of x, psi of x, equals e psi of x. And the idea is to integrate this equation from minus epsilon to epsilon, and that's epsilon is supposed to be a small positive number. So you integrate from minus epsilon to epsilon the differential equation and see what it does to you in the limit as epsilon goes to 0. That's what we're going to try to do. So what do we get? If you integrate this, you get minus h squared over 2m. And now you have to integrate the second derivative with respect to x, which is the first derivative. And therefore, this is the first derivative at x equal epsilon minus the first derivative at x equals minus epsilon. This is from the first term, because you integrate dx, the second, dx squared psi is the same thing as dx ddx of the psi dx between a and b, and the integral of a total derivative is d psi dx at ba I think people write it like this, A to B. Evaluated at the top minus the evaluation at the bottom. Now the next term is the integral of psi times v of x. So I'll write it plus the integral from minus epsilon to epsilon dx minus alpha delta of x psi of x. That's the potential. Now we use the delta function. And on the right-hand side, this would be E times the integral from minus epsilon to epsilon of psi of x dx. So that's the differential equation integrated. And now we're going to do two things. We're going to do some of these integrals and take the limit as epsilon goes to 0. So I'll write this minus h squared over 2m limit as epsilon goes to 0 of d psi dx at epsilon minus d psi dx at minus epsilon plus, let's think of this integral. We can do this integral. It's a delta function, so it picks the value of the wave function at 0, because 0 is inside the interval of integration. That's why we integrated from minus epsilon, to have the delta function inside. So you get an alpha out, a psi of 0, and that's what this integral is. It's independent of the value of epsilon as long as epsilon is different from 0. So this gives you minus alpha psi of 0. And now the last term is an integral from minus epsilon to epsilon of the wave function. Now the wave function is continuous. It should be continuous. That means it's finite. And this integral of any function that is not divergent from epsilon to minus epsilon to epsilon, as epsilon goes to 0, is 0. Any integral of a function that doesn't diverge as the limits of integration go to 0, the area under the function is 0. So this is 0, the limit. And this thing goes to 0. So we put a 0 here. So at this moment, we got really what we wanted. I'll write it this way. I'll go here. And I'll say minus h squared over 2m. And what is this? This expression says, calculate the derivative of the function a little bit to the right of 0, and subtract the derivative of the function a little bit to the left of 0. This is nothing but the discontinuity in psi prime. You're evaluating for any epsilon greater than 0, the psi prime a little to the right, a little to the left, and taking the difference. So this is what we should call the discontinuity delta at 0, at x equals 0. And this is for discontinuity of psi prime at x equals 0 minus alpha psi of 0 equals 0. And from here, we discover that delta 0 psi prime is equal to minus 2m alpha over h squared psi of 0. This is the discontinuity condition produced by the delta function. This whole quantity is what we call delta 0 of psi prime. And what it says is that, yes, the wave function can have a discontinuous first derivative if the wave function doesn't vanish there. Once the wave function doesn't vanish at that point, the discontinuity is in fact even proportional to the value of the wave function at that point, and here are the constants of proportionality. Now, I don't think it's worth to memorize this equation or anything like that, because it basically can be derived in a few lines. This may have looked like an interesting or somewhat intricate derivation, but after you've done it a couple of times, this is something you'll do in a minute or so, and you just integrate and find the discontinuity in the derivative. But that's a formula there, and that's a formula for a potential minus alpha delta of x. So if somebody gives you a different potential, well, you have to change the alpha accordingly. So let's wrap this up. So we go to our case. Here is our situation. So let's apply this. So what is the value? Apply this equation to our wave function. So what is the derivative at epsilon? It's minus kappa a e to the minus kappa epsilon. That's the derivative of psi on the positive side. I differentiated the top line of this equation. Minus the derivative on the left side. This one, the derivative. So this is kappa a e to the kappa epsilon. No, kappa minus epsilon. Again. So that's the left-hand side. The right-hand side would be minus 2m alpha h squared psi at 0. Well, psi at 0 is a. So that's what it gives us. And we should take the limit as epsilon goes to 0. So if this is going to 1, both of them. So the left-hand side is minus 2 kappa a, and the right-hand side is 2m alpha over h squared a. So the 2's, it's also a minus, I'm sorry. So the 2's cancel. The a cancels. You never should have expected to determine a unless you try to normalize the wave function. Solving for energy eigenstates will never determine a. The Schrödinger equation is linear. So a drops out, the minus 2 drops out, and kappa is equal to m alpha over h squared. So that's it. That's great, because kappa is just another name for the energy. So I have kappa m alpha over h squared. So that's another name for the energy. So let's go to the energy. The energy is h bar squared kappa minus, minus h bar squared kappa squared over 2m. So it's minus h bar squared. Kappa squared would be m squared alpha squared h to the 4th, and there's a 2m. All these constants. So final answer, E, the bound state energy, is minus m alpha squared, or minus m alpha squared. The m cancels over h squared, minus 1/2. So back here, the units worked out, everything is good, and the number was determined, this minus 1/2. That's your bound state energy for this problem. So This problem is instructive because you basically learn that in delta functions, with one delta function, you get a bound state. If you have two delta functions, you may get more bound states. 3, 4, people study those problems, and you will investigate the two delta function case.